So, hello everyone, and welcome to the Web3 Devs Underground. My name is Amit Shilo, and I am managing our wonderful community alongside our amazing team of volunteers and supporters. We're honored to have you all with us today. Before we dive in with our amazing guest, I would like to briefly introduce you to our community. We are the Web3 Devs Underground, and we are a community of developers and builders founded on open source values by Shauli Redjuan and Roy Yosherov. Since our inception 4 years ago, we have consistently hosted in person and online events, bringing together some of the brightest technical minds in the space. We're committed to delivering top tier technical content to the global Web3 community. We're thrilled to have you all with us today. To stay in the loop for future events and updates, please join our main group on Telegram. All the important stuff is happening there. And I encourage you to follow and subscribe to all our platforms. We're active on Luma, Meetup, X, YouTube, and LinkedIn. And you can find everything on our website at web3devs.org or by scanning the next QR code. Give me a sec. That's it. The next QR code on the top of the screen. And there you can find all our previous events and recordings, and also all our socials. A special thanks to our community sponsor, Masterkey VC, an early-stage venture capital firm focused on infrastructure and deep tech across the Web3 ecosystem. With a team of 16 world-class cryptographers and several technical experts, led by managing partner Shauli Redjuan, Masterkey operates across all major crypto hubs. And now, without further ado, let's kickstart today's deep dive. Today, we're tackling a massive issue, MEV. It is the hidden tax on every DeFi trade, and AMMs are ground zero. But if transaction ordering itself could be redesigned to be fair by default, if you're building or auditing DeFi protocols, today's session is straight to the core of how value actually flows on-chain. We're incredibly lucky to be joined by our expert today, Dr. Nir Chemaya, assistant professor at Ben-Gurion University. Nir is going to break down CLVR Ordering, a mechanism that rethinks how AMMs sequence transactions and eliminate sandwich attacks by design. He will talk us through the math behind fair ordering, how CLVR compares to existing solutions like SUAVE, and what this even means for the protocol design to move forward. Let's bring our speaker up. Just a sec. Hey, Nir.
Hey,
Great
thanks
to see you, man.
introduction.
So, welcome to the underground, Nir.
Thank you. So it's very nice to be here. Thank you for the community for inviting me to give this talk, and I hope you will learn something.
Definitely. So I'll have you share your screen.
Great. Yeah.
Awesome. So why don't you start with the short intro about yourself, and we would love to dive in.
Yeah, sure. So my name is Nir Chemaya in Hebrew, as Amit spell my name Nir Chemaya. So my background is that I did my PhD at UCSB, mainly on blockchain and decentralized finance. I had a very big luck to work with the biggest expert in computer science, which is Dalia Malki, and also in the econ side, Rod Gerrat, that both work in blockchain, econ, and computer science. And I'm trying to follow them and kind of learn as much as I can about decentralized finance. And today I will speak about transaction ordering and the Clever project. However, my main goal here is to give you a sense about what I think is interesting in DeFi, which is AMM, and in my point of view, AMM will be the next way that we will trade, and it will replace the order book mechanism. But in order to actually understand what Clever is trying to do, I will start with a brief explanation about what is AMM, why transaction ordering matter, also in traditional finance, and then we will dip into Clever. Feel free to ask questions, and that's it. Something that I'm missing, Amit, or we can start?
Go for it. I can't wait.
Perfect. Okay. Yeah, and sorry, I just see my slides. So if you think that there is something bad with the audio or video, just let me know, okay? So I will give just like a motivation why I think DeFi is so kind of fascinating. So in decentralized finance, what is nice is that using blockchain technologies, we can execute transactions in a transparent way that everyone can see all the transactions, everyone can see what everyone is doing immediately with a finality. Another thing that I like in DeFi is that blockchain networks such as Ethereum that allow you to execute codes and smart contracts give us the opportunity to do automated transaction, permissionless transactions, which we will explain later with how AMM works. However, one issue or not issue is that blockchain has no like regulation about or at least now in most of the blockchains like Ethereum, about who can use the blockchain, what is the rules about ordering transaction, MEV, and stuff that we will discuss later. So this is something that can create problems. And if we go specifically to decentralized exchanges, so in decentralized exchanges like which is the new decentralized way to trade, there is an innovation that is the AMM markets, which I will explain shortly. And why this market is so interesting is that the trading volume is insane. It's increasing every day. It's billions of dollars. And beside just cryptocurrencies, more and more people are also using tokenized stocks and stuff from a traditional market, so you can trade basically everything on AMMs. However, there is the issue that due to the regulation problem that I described before, there is some price manipulations techniques that can appear on decentralized exchanges. One of them is sandwich attack, which I'm also going to discuss, and that's something that we want to have in mind. And just to have a sense, sandwich attacks annual profit is reducing over time because there is some improvement in the space, but it was a big deal, like 100, 200 million annual profit. I just want to clarify that the 1 billion volume is not annually, so it's not that currently 10% of the transaction are sandwich attack. It's much less, but still there is a market of sandwich attacks. But this can give you a sense why transaction ordering will be something that we want to take into account in decentralized exchanges. So let's speak about decentralized exchanges. So a little bit history. So basically the idea is that we want to allow traders, users to trade in a decentralized way. Now, the basic question that you can ask is, okay, limit order book, which is the way that stock market works, is a mechanism that works well, and we know a lot from econ literature and finance literature that order book is the efficient way to create a trading environment. It has a lot of benefits. So if we just worry that it's centralized because Robinhood or whatever centralized exchange, Coinbase, whatever, that run the book as some centralization power, so we can just copy paste order book and implement it on the blockchain. But the problem of doing that was that it's very costly to have order books on the blockchain. There was previous attempts to do it and all of them fail. And the reason why it failed is because in order to operate a limit order book on the blockchain, you need to, anytime that user want to update their bid, offer, or whatever, they need to execute a transaction or update the information on the blockchain. And any time that you want to do such an operation, you need to pay gas fees. So it can be very costly to do everything on the blockchain, and that's why it failed. And then we came out with some idea in AMM, the automated market maker mechanism, which was one that mainly adopted, which also known as liquidity pools. And this is the new innovation way to trade in decentralized way. And I will explain how it works recently. And as I mentioned, there is a lot of adoption recently, people speaking about that 20 years from now, 10 years from now, when you will trade in Tel Aviv Stock Exchange or in New York, everything will be with AMMs. Okay, so now let's explain how AMM works. I will want to kind of give credit to Andres Park for this kind of illustration. So basically the idea of AMM is as follows. Blockchain users can deposit two types of tokens, let's say USDC and Ether, to a liquidity pool. I mentioned Uniswap, but the concept of AMM is from many different protocols and not just Uniswap, and so it's not really matter which protocol you can think in mind, but you're going to deposit this token as a liquidity provider in one of the protocols. But basically what you're going to do is you're going to deposit these tokens in a smart contract. So that's why you see like kind of a code. This smart contract then will all these deposits, these tokens, and will basically have a code that said that any trader that want to withdraw or deposit one of the tokens and swap it for the other token can do it only if and only if the ratio between the product of the two tokens in the pool must be maintained and equal to a constant number. And what this basically means is that it's creating a price mechanism, which also people know as the bonding curve, which what is nice and that's why like economists and finance guys like this kind of feature is that the more people want to buy one token relative to the other, the marginal price will increase, will make it be more expensive. And it's a basic demand and supply mechanism that the more that there is demand to one token and there is less supply, then the price, the exchange price will go up. So this is the AMM kind of concept. So if we want to go a little bit more to the math, so the idea is that you have two tokens, we can call them X and Y. The product between them equal to a constant number K. And then you can think about it that in each point of time, the ratio between the two tokens in the pool, which is the amount of token Y divided by X, will be what we call the marginal price or pool price, which represent the current ratio that you can trade one token versus the other. When a new trader wants to interact with the smart contract, so basically if you go back to this illustration, it's this guy, if you want to trade with the pool. So we can say, okay, I will give to the pool that amount of token X, let's call it delta X. However, to make like a kind of a profit for the liquidity providers, you need to pay them fee. So you will pay to the liquidity providers pool fee, protocol fee, which is going to be F. So you can think about it that 1 minus F will be what will left over for the trader to swap in to the pool. So that's what you're going to add to the amount of token X in the pool. And the idea is that the product of the new amount of token X in the pool must be in a way that if you multiply it by the amount of token in the pool pre-trade minus how many tokens you will take out from the pool must be equal to K to maintain this ratio. So if you solve this equation, you can calculate for any trade swap that a trader will enter this amount of tokens to the pool, how many tokens Y the trader will get out, which is basically the trade. And this is kind of the solution to this problem, and then you can basically calculate what was the effective price for the trader, which will be the amount of tokens Y that the trader gets divided by the amount of token X that the trader gave up. This is basically the idea about AMMs. And if we go back to the idea about the order book, so what you can have in mind is that now, instead of paying a lot of gas fee to update every time that you want to bid for a trade in the order book, you just pay one-time gas fee to the smart contract, and you right away swap up the tokens that you want, and that's it. It's automated. It's not going to include a lot of like matching and order book kind of cost. It's very straightforward. But what the three main takeaway for AMMs beside that is, as I mentioned, one benefit of AMMs is that the more people want one token, let's say token X, then they actually will trade it for token Y. So the amount of tokens X in the pool will decrease, and it means that the marginal and the relative price between token X to Y will be more expensive. Another feature is that big transaction will have a bigger price impact. And another feature is that the more liquidity in the pool, the price impact is lower. I just want to show you.
Sorry about that. We had a problem. In the meantime, if you have any feedback, we would love to hear it in the comments from you. It will take a few minutes for Nir to come back. Oh, yes.
Oh, sorry.
Hey, Nir, no worries. Just share your screen again, and we'll continue from where we stopped.
Yeah, so, okay. Can you see the, okay, let's see, the AMM game?
Not yet. I see a white screen now. But I do see your mouse. Oh, now I can see something.
Okay, you see the interactive
yes.
learning? Okay. So basically, I just want to show you, it's kind of a illustration of how AMM works. So imagine that you have a AMM with 1,000 token X and Y, florins and guilders, whatever you. So what you can see here is that this show you like, if a trader want to swap florins to guilders, you can see that for the first 250 florins that you're going to give to the pool, after that you're going to have 1,250 florins in the pool after the swap, and for simplicity it's without liquidity pool fees. And then the amount of guilders from the pool will be lower because this is what the trader will swap out. And what you can basically see here, and that's what I want to show you, is that if the marginal price in the pool in the initial point was 1-to-1 ratio, the more florins you take from the pool, this exchange rate is increasing. So this is showing you the concept of the marginal price, that the more you trade one token versus the other, the exchange rate is worse and worse or more expensive. And also you can see that a big transaction has much more price impact than a smaller one. But something else that I want you to have in mind, because we will discuss it later, is that if you have two traders, so if the first trader will trade 650 tokens from the pool, it will update the pool ratio. So the next trader will right away we will face with a different exchange rate, which is more expensive. So the order of the transaction matter. So if two traders want to trade with the AMM, and let's say both of them want to sell florins, each one of them want to be first because the order matter. The first trader will get more guilders, the other token out, so the order matter.
Just so I understand, Nir, in the case that the first trader wants to do just the opposite, like instead of florins he wants guiders, then the price will be better for the second trader?
Exactly, yeah. So Amit, it's a great point. The exchange price will move to one direction versus to the other. So if we're speaking about opposite operation, so indeed, if someone wants to send florins and I want to buy them, I actually want to be the second, because the guy that will sell florins will make it that I will get more guilders. I will get more florins if I will sell guilders after him. So it's right. It's depend on the direction. But for now, I want you to think about more about most of the time in a competitive market, you can think about it as the information release. So there is a new information release. Everyone know that now Tesla stock will be better because something good happened. So everyone has the information that they want to buy Tesla stock, and everyone want to buy in the same direction. But you're right that if it's in the opposite direction, then you want to be second.
No, I was thinking about it like in the context of if I have knowledge of, let's say, as a centralized exchange or anyone using some kind of this technology, and they know 3 different people want to buy, like 2 want to buy florins and 1 wants to buy guiders. So me ordering them in a specific order can save a lot of fees or change the price for each one of them, basically.
Exactly. And we will show more about that in the CLVR ordering, but exactly. Awesome. That's all the idea, that when you have a lot of trades, the order matter, and you can influence everyone in a good way or in a bad way, whatever your interests are. So if you want to make them pay more, you can make them pay more. If you want them to pay less, you can make them pay less. Yeah, exactly. Okay, now sorry, let's see. Try to see. Can you hear me?
Yeah, I can hear you. Too many windows, I guess.
Yeah, no, yeah, too many windows. Okay, so let me go back to the. Okay, let's go back to the results. Perfect. No, it's jumping to the conclusion. Not good. So, yeah, can you see the Flash Boys slide? Yes. Okay. Now let's go a little bit to speak about transaction ordering in general. So this is a very nice book. If you have time, you can read it. The Flash Boys book. Basically, here they describe some like mechanism and idea that back then I don't remember exactly, but many years ago when there was no internet and telephone, you can think about there is the same stock, you can trade it in New York Stock Exchange and Chicago Stock Exchange, the same stock. Now imagine that there was in New York Stock Exchange, there was a release of information in one day that Tesla stock go up because they have a new innovation. Or back then it was like Coca-Cola stock or whatever. So the idea is that if you can trade both stocks in New York Exchange and Chicago, and you already have this information in the New York Exchange, so in the New York Exchange, the price of the stock goes up, but it will take time until the information will go over to the Chicago Stock Exchange, and then you can buy the stock in a cheaper price because the information there is not there yet, and then the price will adapt and be the same as the market. So there was kind of a competition. It's competition about speed. how you can go fast from New York to Chicago, buy these stocks and have the profit. So it started with horses, whatever, trains, cars. Once we have internet, people thought that that's it, it will kill the competition. However, this is not reality. So the competition now is in a very high speed of having better computer, better internet, putting your office of the brokers next to the stock exchange, so you have like 1 second more from the regular trader to buy stocks once there is information relief. So this the idea. And once there was this idea that transaction order matter and people can get money and benefit from this order, so high frequent traders are basically using that, and there is an arm race. And this kind of paper try to explain that we can't really kill this problem by thinking about that a better technology will eliminate the problem. The way to deal with it is to have a different trading mechanism that speed has no value. So this paper offered a new way. Instead of using order book mechanism as is to use something that they call batch auctions. And in batch auctions, the idea is that all traders have a block or time interval that they can say if they want to buy or sell a stock. But the execution of all the transactions will be in one batch, and everyone will pay the same price. So in that case, if you are slightly faster, it has no value because everyone will end up trading the same. So that's the idea to deal with the flash boys. Now, in DeFi, after years later, there was the Flashboy 2.0 kind of paper, which tried to explain, okay, in DeFi, we have the same problem. There is a value to the order of transaction of AMM, as I described before. You know that if you are before other traders, you can have a benefit. So why not to actually use this benefit? And that's why we have the problem in AMM that we see sandwich attacks and other front-running manipulations that we can see on AMM and decentralized exchanges. Now, the main question today in the paper was how we can come up with a new mechanism to order transactions to deal with the Flash Boys 2.0 problem, but in a way that's going to be good for the blockchain environment. And this is what we will try to do with Clever. Questions so far?
I have one maybe stupid question, but is Flash Bots taking like inspiration from Flash Boys? Like the name, the name of Flash Bots?
Good point. Probably yes. Especially because I don't know if you know, but Philip Dayan, which wrote this paper and was the main contributor, I guess, because he's first, is the founder of Flash bots. So
Awesome.
I guess this is the answer, but we can ask Phil. Okay, so about auctions. I will now try to give some related literature that try to give some ideas, because we are not the first, and there is many that thinking about how to improve transaction ordering on AMMs and blockchain in general. So one way to think about the problem and deal with it is to say, okay, there is an economic value to trade first on AMM. So it's ideal to come up with an auction. So basically the auction will say, okay, if you want to be the first to trade with the AMM in any block, pay more gas fees, priority fees, and then you will be first. Okay, so this is one way to deal with this problem. And second way to deal with the problem or to more protect users is that besides that there is a economic benefit to trade first, there is also one main concern, is that traders can manipulate, bots or whatever, or sophisticated traders can manipulate regular traders by implementing sandwich attack. So what you basically do in sandwich attack, the way that you can think about it, is I know that Amit want to buy Bitcoin, okay, from a liquidity pool of Bitcoin and a stable coin. So I'm saying, okay, I know that the AMM mechanism work in a way that the more you trade with the AMM, you push the price up. So I can say, okay, if I have the power to decide the order of the transaction, I can buy Bitcoin from the pool before Amit, push the price that Bitcoin will be very expensive, and then Amit will execute this transaction. So instead of getting 1 Bitcoin for 1,000 stable coins, now we will need to pay 5,000 stable coins for the same Bitcoin or whatever. So in that case, what will end up is that the attacker can say, okay, I will put the transaction before Amit. Amit will get much less than he need. And then we're going back to the point that I can trade in the other direction and get a lot of Bitcoins out or whatever. So when you do this sandwich attack, and you can dive in and learn more about it, you will see that you basically can earn a big profit on the back of the trader. So today, in order to fight this manipulation, what you can do is you can set a slippage tolerance settings when you send transaction to AMM, and you can say, okay, I am willing to trade with the AMM if and only if I get at least X amount of the token that I'm going to buy or whatever. So if Amit will try to sandwich me, the transaction will fail if he will try to take too much profit on my back. And in that way, it will be that Amit will try to attack me, but my transaction will fail. So it will end up that it's not going to be profitable to Amit to attack me. So that's why you see that these settings that Uniswap and other AMMs are implementing pretty much improving the protection against sandwich attack, and we see less and less sandwich attacks.
I have a question, and we have a question from the audience as well on that. First one, my question is, how expensive is doing a sandwich attack is? Do you only need to pay the fees for that, or are there any other costs for that?
Okay, good question. So basically, you can solve it mathematically. It's not easy, but the way that you can think about it, there is two main costs when you do slippage attacks. One is you need to pay gas fees, but because you need to do front run transaction and background transactions, so you need to pay twice gas fees. And beside the gas fees, you need to pay for the liquidity providers swapping fee, which each pool has the different fees. So this is the summation of all fees. This is in case that you have the liquidity available. If not, you also need to take flash loans to have enough liquidity to run the attack. So basically, when you think about all these costs, you can solve like a game theory style problem, and you say, okay, this is the amount of cost that the attacker needs in order to attack me. So if I set my slippage in a way that the maximum benefit that the attacker can take from my transaction will be equal to this set of fees that he need to pay, you can basically make it be that it's going to be very low likely that he will attack you, or it's
going to be, he will only be able to lose money on it.
Exactly.
Awesome. And the question from the audience on sandwich attack, I'll put it here on the screen. It's from Yoav. Is it sandwich attacks also common in centralized exchanges, or is it only something for decentralized exchanges?
Good question. So on paper, if there is a centralized exchange that running AMM, which the way that you can think about it is that I'm not really know. So, but there is like, there is all these Coinbase companies that try to adopt blockchain technologies, so they on paper can run AMM in a centralized way or on their app. So maybe they can do it. I'm not sure, but definitely on regular stock markets, and this is go to the high frequent traders, there is no sandwich attacks, but there is a kind of a front running, even that it's illegal, but there is kind of there is a reveal of information that user knows. So for example, think about it that in Robinhood, when many small users send their transaction to Robinhood as their broker, before this set of transaction is implemented on the stock exchange, Robinhood need to share this information with a broker or whatever intermediation that's going to facilitate the transaction. So this information is valuable. And once someone see that there is a lot of call options to do X or Y, or there is many people demand to buy Tesla stocks, people can benefit from it. So there is regulation to make it be that there is no benefit. However, I think that there is some finance papers that show that some people benefit from it. So you can think about it. There is another ways that people benefit from users' transactions or intended transactions, if it makes sense.
Yeah, I think it answers that, but you have you're more than welcome to comment more.
Yeah. Okay. So yeah. Something that is relatively new, which could be a good solution, is the batch auctions on AMM. So basically, the idea is that there was, as I mentioned, there was the Buddhist paper that showed maybe we can batch auction and transaction on order book. So in that spirit, you can do the same on AMM. So what basically you're going to say, there is a block, there is 5 transactions that pending to execute on a blockchain. Let's batch them together to one big transaction, implement them on the AMM, and then all the traders will get the same execution price. It's still not really with high adoption. I think there is in CowSwap something that they try to implement it. I'm not sure if it will take off, but one problem with batch auctions on AMMs and blockchain is that there is one manipulation that you can do in batch auction, which is I want to manipulate traders. So I see there is a batch with 10 transactions, whatever price they need to get because all the transactions are bonding together. So what I can do is I say, okay, I know that after I will insert my transaction, it will influence all the traders' execution price because I can edit my transaction, and if the transaction is so big, I can influence the batch price for everyone. So this is one issue with batch auctions, which later I will explain why I think CLVR is kind of better in that sense. But still, batch auction can be a very good solution as well, and it's still early to judge. So basically, there is a lot of issues with MEV. I'm specifically focusing today on AMMs, but there is a lot of problem with MEV. But I think this paper is very good explaining one issue that we have in the consensus layer. So there is ways that you can have rules about how to execute transaction on the consensus layer. So think about Ethereum. In Ethereum, you can say, okay, let's execute all the transaction in a way that is first come, first serve. But the problem is that a good order that is fair for lending protocol or for swapping transaction is not necessarily what will be fair in a AMM environment. So this paper tried to show that ordering rules need to be application specific. We need to come out with ordering rule that we not really implement on the consensus layer, but more about in the application layer. So we need to have an optimal way to order transaction for AMM and a different way to order transaction for lending protocol or whatever. And we're going in that direction. So the most related literature to us is the GSR, which is I will give more like a kind of a specific explanation how it works, but it's basically saying that there is a way to order transaction on AMM following a very basic rule that is allowing to prevent sandwich attack and can also improve price stability. And we will show like our ordering rule, which is clever, which we think is slightly better than the GSR, but the GSR was the first kind of rule, and it's also very good one. So that's the kind of the background, because now we can start introduce the paper. So questions before we move to the clever kind of idea?
None for me in the meantime. Yeah.
Okay, good. So the recent question is, when we came with clever, we first say, okay, what is order that is going to be good for the entire traders? Okay, what is going to be the optimal for the traders? So when we thought about the traders, we say, okay, when a trader come to interact with a AMM, they have two things in mind. They say, okay, currently the current price of the pool is whatever, so they know what is the current price in the block, so that this is for them the state of the world, and they will send their transaction accordingly. So they mean that when they see this price, they are willing to buy for this price. So they think in mind, I am going to be the first to trade with the pool, and that's what I see as the state of the world. So given that, I want to get the closest price to this like initial price. So that's why if we're going to reduce the price volatility, or you can call it price stability, most of the traders will get plus minus the same execution price as the initial price. So this is the objective that they get, and what it's also going to imply accordingly is that we will have less issues with transaction failures and problems with slippage protection, because if you get plus minus what you should get if you trade first with the pool, so there is no way the transaction will fail, because this is what you send your transaction accordingly. So what we will do after is we will say, okay, we will have an objective function. We will try to order transactions in a way that's going to minimize the price volatility. So we want to find the optimal way to do it, that it will be not kind of expensive in terms of computation cost. And after coming with the way to do it, which is clever, we will explain how it will influence the market in some other aspects, like how traders will trade when this is the ordering, if they're going to split their transactions, in terms of the blockchain itself, how the block size, how many transactions are waiting for execution, help or not for achieving this objective. So that's the main contribution of the paper. We will come out with clever, which is the Clever look ahead volatility reduction. I will explain how it works. We will show that it's very good in achieving a almost like minimal price volatility and reducing price transaction failures. We will go ahead and explain a little bit about block size and its impact on Clever, transaction splitting as well. And we will show some like empirical results about the benefits from Clever. Sorry, I don't know why this format, the numbers are sometimes messy, but okay. That's the plan. So let's kind of go back to the model of AMM and let's kind of explain a little bit the settings. So the idea is that we have a AMM. Let's think about the basic version 2 Uniswap style. And when we have this pricing rule, as we mentioned, anytime that someone wants to trade with the pool, he will insert one token to the pool, get the other token from the pool, and the order will change the state of the pool. So what is basically the ordering problem is to say, okay, we get set of transactions that are in the meme pool that are waiting for execution. So you can think about it. I have transaction A, someone wants to sell token A. I have transaction B, so beta, someone wants to buy token B. I have gamma, where whatever. I have like set of pending transactions. Some of them are buy, some of them are sell. So buy or sell, you can think some of them want to give up token X and get token Y, and some the other way. And basically the idea is we want to find the optimal order that's going to take this set of pending transaction and then map them to a specific order that's going to give the most desirable way for us, which will be to reduce price volatility. Now let's give an example to show why order have a direct impact on price volatility. So let's, for simplicity, think about a very basic pool, which you have two tokens, X and Y, and there are the amount of the tokens is equal, so the initial price is 1-to-1 ratio. Think about stablecoins pool. You have USDC and USDT. So basically, there is 4 transactions of 10 units of each of them. 2 are buy and 2 are sell, so it doesn't matter. So the idea is, let's see what's happened in different orders to the price volatility. So if you start with doing 2 transactions that are, let's call them buy, the blue and the green, and then you do the purple and the orange, you see that the amount out that the trader gets going to have much greater volatility, okay, than if you alternate between buy, sell, buy, sell. And this is basically the idea, is that the order matter to the traders, and the way that you're going to order the transaction will have different outcomes in the individual level of the traders, but also if you look at it as the in the aggregate level. So here you have a greater price volatility than here, of course. Okay, this is the settings. So in order to think about how to optimally order transactions, we will do kind of think about it as kind of a game that we say, okay, let's assume that we have a social planner. So now put blockchain aside, everything aside, it's just like think about the problem that you have a lot of transactions and you are a social planner that have the power to decide what will be the order of transaction, and you're going to get an objective function. So think about it, economic function, and you want to find the order that's going to minimize or maximize the objection function and give the more desirable result. So the objective function, we say it's to reduce price volatility. So basically what we say is we take the initial prices, P0, the price that the pool start with, and we're going to take each transaction, and after executing each transaction following a specific order, we're going to calculate the new exchange price. So basically this function will give us the average price volatility for a specific order of transactions. So basically what you can do is, if you have n number of transactions, you can go over all the combinations of transactions that you can order this set of transactions, and always you're going to have one specific order that's going to give you the optimal price volatility. Maybe sometimes there is a multiple solutions, so there is few orders that going to give the minimum, but always you're going to have a solution that's going to give you the mean value that you can get. So basically this is the question. This is the objective function, and now you need to find mathematically or whatever to solve it, to find the order that give the optimal price volatility, which is the minimum, because we want the lowest.
So
question?
Yes, just so I understand this, and maybe to simplify it for the audience, it's less math savvy. This is something that has like an analytical solution as well, or you need to run it on a computer each time for the different solutions that you have specific in this specific batch?
Great question. So currently, if we could solve it, so there is no like a solution in terms of mathematical solution. So currently, if you want to pick it, what you need to do is go over all the permutations, and then to pick the best outcome if you want to find the optimal. And what you can see, and this is what we will show later, is that given that it's the difficulty of computer to go over all the permutation is RDN, in a sense that it's increasing very, very rapidly. So
it's n or n squared? Like, what's the complexity?
It's RDN, it's a PN. So it's basically it's in a sense that you can think about it that after, just to give you a sense, after 12, if you have a set of 12 pending transaction, it's already take few minutes to a computer to solve. And when you move from 12 to 13, it can even take 1 day, 2 days, whatever. So it's basically become unsolvable, at least when you have more and more transactions. So that's why we need to come out with an algorithm that approximately gives a good answer, but with much less computation cost, because it's not something that you can go over all the permutations.
Okay, do we have this algorithm already, or is people working on that?
So I will show you Clever, which give you the minimum, the approximately price volatility. However, it could be that there is a mathematical solution to find the optimal order mathematically, but for now we try to do it. We think that it's very hard question to solve. But okay. Clever, it's very good. So you will see later empirically that Clever is approximately always give the minimum.
Awesome. And we have another question from Yoav about that. I'll put it here as well. He asks if the permutations are the set of transactions.
No. So think about permutations. It's basically you have the set of the transactions, which is going to be n. And then what's going to happen is that given this n, you're going to have the combination of ordering that you can have. So basically, think about it as exponential in the sense that when you have two transactions, so you have like when you have one transaction, you have one combination. The more transactions you have, you're going to be a very high permutations to go. Permutations, it's all the possible combination of this set.
For ordering this, if I understand correctly. So like 1, 2, 3, 1, 3, 2, and
exactly.
And the more I have, the more complex it becomes.
Exactly. There is more combinations, so the permutation is exploding after 12 transactions. Perfect.
Awesome. Thank you.
Great. So given that it's very hard to go over all the permutation, very costly, so we need to come out with a kind of a way to solve it. So just to give it a sense, when you have a very low amount of transactions and you really can go over all the permutations, so you can see, for example, when you have this set of the transactions, you go over all the permutations, then you can see what is the order that gives the optimal price volatility. So you can have a sense that a good order, in a sense, need to alternate, but it's not very easy to think how to alternate. So you can see that sometimes it's good to do small transactions, sometimes you need to do big transactions. So it's not like very obvious. So now let's think about rules that can approximately minimize this objective function. So now let's speak about GSR. Something nice about GSR, which I will show, it's very easy to implement, and it's very and it's prevent like 3 transaction sandwich attacks. I will just say that GSR idea was to deal with these 2 problems, so that it will be easy and preventing sandwich attacks. So they have nothing in mind about having objective function that you need to minimize. However, it also little bit like, in a sense, it's good also with minimizing price volatility, but not the best. And I will show empirically after. But how GSR works is basically you start with one transaction. It can be buy or sell, whatever. And then if you start with buy, if your price is let's say more expensive than the status quo, the starting price, and you start buy, so if there is a sell transaction waiting for execution, you must pick sell, because you're already going in the opposite direction of the status quo. But if there is no sell option, you need to go to a buy. And the idea is that you always need to kind of repeat of 2 and 3 until you execute all your transactions. To little bit give more like a sense, so it's maybe easier to show an illustration. So imagine that this is the set of pending transactions that we have. So if we follow GSR, we need to start with the transaction. For simplicity, let's start with the first transaction. So the first transaction is, let's call it sell, whatever, it doesn't mean. So let's say if you go below, it's a sell. If you go above, it's buy. So you start with a sell. And then given that you start with a sell and there is buy transaction waiting for execution, so you can do a buy. Now, after doing a buy, again, you are over the initial price line. So there is sell waiting transaction, let's do a sell, and so on. Now it's important. In GSR, if you do a buy or sell, whatever transaction, but you still not crossing the line. So instead of now doing the opposite transaction, because I can do the purple one, but GSR rule means that you must do transaction in the same way, because you can alternate only after crossing the line. So that's why here in GSR, even that you can do the purple, you will do first the brown and then the purple. This is the GSR. Now, the main idea of GSR was to prevent sandwich attack and give traders prices closer to the initial prices. They not have any in mind about reducing price volatility, but you can see that as a second kind of benefit, it's also give a relatively good price volatility. Now let's go to Clever. So what we say is, okay, instead of following GSR, let's have a new pricing rule or algorithm, what Clever will say, okay, you have a set of transactions waiting for execution. Any step, any time, you will take all the waiting transactions and pick the one from all these sets that give you the lowest price volatility. So that's why we call it look ahead, because it's step by step. So if you have 10 transactions in the beginning, you will say, okay, from all these 10, I will pick the one that will give me the lowest price volatility. So I will pick the first transaction. In other words, it means that I will pick the lowest transaction, because the smallest transaction will have the smallest price impact. But when I will pick the transaction after, now instead of 10 transactions, I will have 9. So I will go over all these 9 transactions and then pick the next one. I just want to clarify that in terms of computation cost, it's much more like cheaper or easy to computer to order transaction using Clever than go over all the permutations. I'm not going to go deep into it because it's more like computer science conversation, and it's less my cup of tea, but it's much easier in terms of computation cost. 2 nice benefits of Clever. It's also prevent sandwich attacks. So we have a proof for that in the paper. But what I will show you empirically, and this is very, very nice, is in many different environments, it's almost always give price volatility that is closer to the optimal. So we show you like that we did some tests, and we can see like what is the price volatility if you go over all the permutations, compare it to what Clever gives, and the differences are, you will see it's almost 0. So it's give a very good approximation to the optimal outcome with a much lower computation cost. So how Clever works: when you have a set of transactions, you're always going to check what will be the price volatility after go over all the options. So in the same example as before, you see it will be blue, orange, green, black. But now, and this is the differences between GSR and Clever, it's end up that it's better to do the purple and then the brown. And if you compare between the 2 options, you can see that you can improve price volatility. And there is many cases that you can do it, but this is just one example.
Just asking because I noticed it, and I'm not sure if I'm right. Is the best possible combination here is doing the brown one before the black one?
Exactly, yeah. So
and this is something Clever can't find because it's not in the algorithm?
Yeah, exactly. So sometimes there is cases that Clever give something slightly different, like this example, but you will see that if you compare the deviation in terms of like if you compare the volatility of Clever versus the optimal outcome, and you can see even here is just an example to kind of emphasize but when you will see empirically, you will see that most of the deviations of Clever end up with a very small volatility difference versus to the optimal. But with GSR, you will see that in this case, it's also very similar. You can see the volatility numbers are very similar, okay? But you will see that
how
sometimes...
does it scale, by the way? Like for very big numbers, how do they scale?
You will see everything empirically soon.
Yeah, awesome.
Okay, great. Okay, so now we will do evaluation. So basically after coming with Clever and whatever, now what I need to do is to show you some kind of simulations and analysis to make you trust Clever and see like how it's doing. So basically what we can do is we can run simulations, and the idea that you can think about it, we can run simulations that we have a AMM that we create with token X and token Y. We can generate synthetic transaction flows with different number of transactions, and we can calculate the price volatility, and we can compare it between the optimal order, because we can also go over all the permutations and find the optimal, which we call it the global minimum. And we can also compare our results to GSR, which is the alternative to Clever. So in order to make it be more realistic, we used we did simulations with a kind of realistic AMM. So we picked the biggest stablecoin pool in AMM, which contained 2,000 USDC and USDT. We use distribution of transactions from empirical data, and then we run the simulations. So let's first compare Clever to GSR. Now, something nice is that when we compare Clever to GSR, given that computationally it's very cheap to run Clever and GSR, we could do it for even crazy number of transactions. So basically here, when you see like 5 transactions, it means that we order 5 transactions on the AMM. If you see 1,000, it means that we order 1,000 transactions using Clever algorithm and GSR. And we did it in purpose because we want to see when Clever give better price volatility and when GSR. And we can see something that is trivial is when there is 2 transactions that they are identical. By the way, we use a GSR method, which is mean that you apply GSR, but you always start with the smallest transaction first. So when you use GSR and you always start with the smallest transaction first, it's always will be that when you have 2 transactions, you get the same as Clever. So here you have like in 2 transactions, they give the similar results. But what you can see is that cases when Clever give better price volatility, GSR and tie. And you can see that in percentage. So you can see that, and we did like thousands of simulations for each category. And you can see that it's pretty much clear that Clever is giving better results. And it's not surprising because Clever goal is to reduce price volatility, and GSR has a different kind of agenda. So it's not. I want to defend GSR because GSR is clever and very nice design, and when I compare between them, I compare more in the sense of price volatility, but it's not because this was their objective function. So it's important to mention it. Okay, when you go and compare statistically test about kind of which is better, you can see that statistically, at least when it's become more and more transaction, it's pretty much clear that GSR, Clever is doing better than GSR. Now, what we also can do, which is nice, we can compare both of them to the optimal order, but we can also only do it up to 12 transactions. So just a quick reminder, before I tell you that if you go over all the permutations and pick the optimal order, it's very hard to computer. It's to the computer to do it. It's very costly. So we able with our computer to go up to 12 transactions. So when we go over 12 transactions, all the permutation, and we calculate for like 1,000 simulations, Clever price volatility, and compare it to the optimal price volatility, we can see the deviation of Clever is very low. So it's less than 0.2%. While GSR has more price volatility, it can even go up to 6 or 7 on average. Okay, so this what give us kind of the make us feel more confident that indeed Clever is approximately giving the minimum price volatility. Questions so far?
I have one question on the previous slide. I'm not sure if it's something that is possible to calculate at the moment, but here, like one slide before that. Yeah, awesome. So here, I think the peak here is at 12 transactions, but it starts going down again and to be closer to GSR when you come closer to 1,000. Does this change somewhere or like stabilizes? What happens when you get to 5,000 transactions or 10,000 transactions?
Yeah, good point. So yeah, so good catch. So what we observe is that in this kind of environment neighborhood, if you do more transactions, it's pretty much stable. So I think it means that there is some pattern, like you mentioned, that it's kind of go to the maximum deviation between them or whatever, and then it's arrived to the point that there is some cases that when you have a lot of transaction, GSR is doing better, some cases that Clever, but it seems that it's pretty much arriving to a stabilized point that this is kind of the ratio. So if we do like 1,500, we get very similar results. So it's not that it's, in other words, it's not that we see like starting reduction that worth exploring. It seems that this is kind of the place that it's become more stable. If it makes sense.
Yeah, it makes sense. Just wanted to understand.
Okay. So this is another example as we showed before, but the idea is to show another cases when GSR can have a very high price volatility relative to Clever. So for example, sometimes when you have a lot of small transactions, okay, and you have one big transaction in the end, sometimes it's not really beneficial to alternate as the GSR doing and do buy and then sell, because once you do a sell, you kind of pushing the average price a lot down. Of course, I will say that everything here we're doing the aggregate level, and we're thinking about price volatility in general and in average. So some cases you can tell, hey, but if I compare this set of ordering to this, some of the traders like trader 2, 3, 4, and 5 are doing better under Clever versus to GSR. So what I want you to have in mind, everything here we think about an order that in the end consistently give better price deviation than the other. Okay, so don't take one example or thinking about one trader as a way to think about it. Think about the broader picture. Okay, failure rate, which is nice. So one benefit of having a transaction ordering rule, either GSR or Clever, but both of them give very nice results, is that if we going to have transaction ordering rule in AMM, and let's think about it, that AMM are scale up. So one issue, I think that there is no so many papers about transaction ordering on AMM currently, is that even that the volume is massive, there is no so much traffic in terms of transactions. So just to give a sense, currently in Ethereum, even the most active liquidity pools have less than 3 transactions, 5 transactions in a block. So when you have a very low amount of transaction in a block, like you see here, transaction failures, price manipulations have less power. However, if you have kind of more like future kind of eyes about what will be like 10 years from now, or if you scale up the number of transactions, you can see that currently if you take an AMM and you increase the number of transactions to 100, and each transaction going to have here we put 0.5 slippage tolerance as the default in Uniswap, for example, or used to be. You can see that if you do random ordering, the more transaction you have, you're going to have crazy failure rate. So it means that, for example, let's take 10%, 10 transaction, you're going to have 8% of the transaction going to fail because of slippage issues. Okay, while if you're going to have a ordering rule like Clever or even GSR, you can reduce it to almost zero, like very low, so it's less than 1%. So it can be a very big deal once we have more adoption and more transaction on AMMs. That's what I want to say in mind, but you can see that having a transaction ordering mechanism also really going to be good for transaction failures. Because I don't want to spend too much time, I will go briefly about, mention 2 stuff that are, I think, important to have in mind. So here we did like a very nice kind of a game or simulation that we said, okay, hypothetically think about you're going to have an AMM, you have 100 transactions waiting for execution, and you as a social planner have the power to decide if you're going to execute all transactions using Clever in one big batch. So you can see here, if you take all the 100 transactions and you batch them together, what will be the price volatility? And what will happen if you're going to split them to smaller blocks. So for example, if you think about the here, can you see what I'm pointing around? I mean,
yeah, this is like the average.
Yeah. So yeah, so exactly. So you can see here it will be what will be the average price volatility if you take the 100 transaction and split them to blocks with 10 transactions each. So you basically take the 100 transactions, split them to small batches of 10 each. And what you can see that having a big block has a good benefit because you can more alternate and play with the order of the transactions to improve the price volatility. I will say about that, if you think about this question and more, is that it's there is a trade-off, because if the block is bigger, so it means that the finality of the execution of the transaction will be slower. So there is some you need to think about how you want to design it in a way that the block size is optimal. So I'm not pushing that necessarily you need 100 transactions per block, but I can also push that one transaction per block, like first come, first serve, is not also optimal. The second point that I want to say a little bit, but I'm not going to dig in so much, is when you have a transaction ordering mechanism like CLVR, there is a benefit to split transactions. So the way that I want you to think about it is the easiest way. Imagine that I want to trade a big transaction and Amit want to trade a big transaction. So if both of us going to trade with an AMM with big transaction each, so on average, if you take Amit first transaction and mine second transaction, you will see that on average both of us get the same kind of that the execution price on average will be the same, but you see that there is a big volatility. What this big volatility means is that if Amit is buying 1 million stable coins of USDT, and I am going to do the opposite direction after him, so he will buy in a very, let's say, not attractive price, and I, as a second trader, can get a much better execution price. So in order to reduce the risk and not make it be that one is getting a much better execution price relative to the other, what you can do is if you kind of split the transaction. So if each one of us will split the transaction to, I don't know, 10 small transactions, you can see that this will create a much more kind of a low price impact, and the price volatility will go down to very low. And basically this is the idea that under CLVR and price ordering rule, there is incentive to split your transactions, but bear in mind that it's also dependent on the gas fees. So if for each transaction you need to pay gas fees, so probably it's not going to be optimal to split it to 1 million transactions that you need to pay $1 fees for each transaction, and it will be very expensive to do. But there is a sweet spot that maybe splitting a big transaction to 5 transactions can give you better off than doing one big one. So that's in mind. We have in a paper some analysis that show that on average all traders are better off of splitting transactions, and that's it. So I think, because I want to leave time for questions in the end, I will go now briefly on 2 very nice features. So first, we test the water and we checked empirically. So what we did is basically we took one of the biggest liquidity pools of Uniswap version 2. We took empirical trading data, and this empirical trading data give us what we call the price volatility, okay, of a specific order that already actually was implemented on the blockchain. And then we can compare the price volatility of those orders to the maximum price volatility and minimum price volatility, and get a range of how good or bad those orders are relative to the mean and the max. And what you can see, and this is what we try to push with CLVR, is that even currently with a very low amount of transactions on Ethereum, you can see that the current ordering is not so efficient in terms of price volatility. It's around 50%. So remember, 100 is the maximum price volatility, 0 is the mean. And if you're going to implement CLVR, And that's what we did. So we kind of say, okay, imagine that we can order those transactions using Clever. What hypothetically could be the price volatility? And we can see that it can shrink to almost zero. And this is kind of the nice feature of Clever. That's it. Okay, now I will say finally that in computer science, when you run kind of these algorithms and you get very nice empirical results, people still will want to get more kind of a sense and tell you, okay, how you can find the upper bound or worst case kind of estimation that can give more sense for someone that want to use this mechanism of what will be the worst case deviation of Clever from optimality. So we try to think about this question. So first we get some kind of very nice but also very intuitive results that we saw that there is cases that trivially the order of Clever is the same as the optimal. So the cases that the Clever is doing the optimal order are that the number of transactions is less or equal to 2. So let me show you here. So you can see that there is 2 transactions. Clever give the minimum price volatility as the optimal order. Also, I want you to bear in mind that you see that Clever is doing well up to 5 transactions and then it goes down, because I will discuss about it later. So it seems that the peak of the deviation is around 5 transactions. So, and when the number of transactions is greater than 2, but all the transactions are in the same direction, also because the way AMM works and the marginal prices go up for each marginal transaction, so it's the minimum price volatility is to execute small transactions first and go to the bigger ones when all of them are at the same direction. But in order to kind of evaluate what is the worst case performance of Clever, so we try to do a lot of simulations and try to figure out which patterns we observe that can give us a sense of what is the worst deviation of Clever from optimality. And as I mentioned before, we saw that around 5 transactions, this is the maximum deviation, and then when you have more and more transactions, it goes down. And the reason why it goes down is that the way that we see it is that the more you have transactions, Clever have more flexibility to order them, which make him be more and more closer to the optimal order. So even if there is deviation, it's very minimal. However, 5, it's still the case that one deviation, one transaction that Clever is ordering not in the optimal order can have much more impact on the entire entire deviation. So we try to kind of explore this 5 transaction environment. So we ran many different simulations with 5 transactions to compare Clever to the optimal order. And what we see is the distribution of deviation is very clear. It's almost very centralized around almost no deviation. And the worst case deviation that we found after running thousands of simulations was around 8%, which is this point. Okay? So we think that statistically it's kind of showing a worst case performance. However, could be that there is some unique cases that it's more, but it seems very promising. And also we checked if the liquidity available in the pool also going to impact this price volatility. So if you have 5 transactions waiting for execution, you still see that price volatility is bounded around 5%. So it seems that the amount of liquidity in the pool has no big impact on the worst case analysis. That's it. So let me conclude and then let's give some time to conclusion. So I think what is beauty in AMM and DeFi many people speak about it, think about it that regulation, it's very costly, and it's a lot of kind of money and resources, and you need lawyers and people to enforce it. And all the idea about blockchain technology is that we say, okay, maybe we can come out with smart contracts and other tools to create a market design, a technology that's going to enforce regulation. And you can think about it clever. It's a way to enforce some regulation to improve ordering rules on AMM. And what is nice is that if you use these kind of tools, it's end up with protecting user, which is the same as regulation, and also improving welfare for all users, which also something that regulation tend to achieve. So this is a new way to think about regulation, in a sense that you come out with market design as a solution for regulations or issues. So just to conclude what we discussed today about Clever, which we show that frequently and approximately gives the optimal price volatility with low computation cost. It's also reduced transaction failures, which is a good feature and something that we want to get. It's prevent transaction sandwich attacks. We give some ideas to think about if you're going to implement Clever in that way or in another. You can also think about what is the optimal block to implement Clever, how many transactions you want to order, or if you want to have some impact on this decision. And we think that if you have a Clever, based on the gas fees environment that traders will trade, if it's L1 or L2, users may decide to split their transactions. And now let's think practically how you can implement Clever on blockchains. So we have few ways to think about it. First, if we move to a play that traditional finance will have AMMs, so they can implement Clever on their AMM environment. So you can think about it as a centralized exchange or whatever that. Amit, can you hear me? I'm just like.
Yeah, can you hear? Did you finish with the presentation?
No, I just want to make sure because I see that my internet connection is okay.
Yeah, no worries, continue.
So think about it. One way to implement Clever is if we will move to the way that this, let's say New York Stock Exchange will have a centralized blockchain that they run AMMs using their blockchain and AMM, whatever. So they can implement Clever on chain, on the centralized blockchain. So this is one way to think about it. Another way to implement Clever is that you can, on the protocol level, so you can use maybe Uniswap version 4 kind of OX platform, whatever, to build in within the smart contract of the AMM, that the smart contract already going to implement Clever on the application layer. You can, on the protocol level, you can think about it. Another way to think about it, that there is more and more kind of papers like Prof that push that can be kind of a validation rules that validators need to commit, and one of them can be Clever. So a validator that want to build a new block will get set of pending transaction and must order them using Clever. So this is the way. This is more in the consensus layer. Another option is that they're going to be a blockchain only for traders. So you can think about Unichain or Hyperliquid. And in the blockchain level, they're already going to say, okay, we only order transaction using Clever or whatever. And so this is basically the idea. Okay, this is linked to the paper, and that's it.
Awesome. Thank you so much, Nir. I have a few questions that we prepared before, and also I'm opening the option for the audience here to feel free to just comment. On YouTube is easier for us, but if you comment, we'll see it and put it on the screen, and that way I can ask Nir. But for now, I'll start with the first thing that were on my mind most of the lecture, but what's happening today in centralized exchanges, not even like in Web3, but like my broker account or in the stock market in general, like how is it handled today? Do they use some kind of algorithm to like order the different like buy and sell order like in the order book, or is it just like first come first served? How does it work in the traditional market today?
Yeah, it's a good question. So I'm just want to clarify that I'm not finance expert, so I'm not really know for like details it. So I don't want to say things that I'm not really know, but I know that in general in order books rules, it should be that the first matching decision will be based on how much you're willing to sell or buy, because this is the main like matching feature. But regarding to your question, if I am willing to pay $5 and you're willing to pay $5, and so then it should be first come first serve. So if my transaction came before yours, it first need to fulfill my $5 transaction and then yours, if it makes sense.
Yeah, totally. And I don't know. I thought about like in Forex or stuff like that. It's super useful to use some kind of similar algorithm to kind of keep the like ranges as still as possible, or to not fluctuate too much. I'm not sure what's happening in the market today in this aspect.
But something that I want to also emphasize, and it's go back to it's more like in the way that people need to think about it, that one pushback always about first come first serve is that even this is not fair in the sense of the internet advantage that you may have to relative to mine. Okay, so I will give you like a very dumb example, but there was the World Cup. There was a World Cup kind of lottery to access to buy a FIFA tickets. So so many times they say, okay, in specific time slot, you can go to the website and then you can have the first kind of permission to buy tickets. So in that sense, everyone is like on the website clicking like in the same second that the deadline is, and you can see that someone that is slight faster, has a slight better internet, is having a big advantage. So it's the same. It's with first come first serve. If you have this kind of blockchains, you always have the problem of speed, that someone have a better internet connection, we will always send this transaction before you or whatever.
Okay, understand. So I'll jump into our questions because we only have 15 minutes left. I'll start with the more technical questions and then go to the questions about you. The first question I have is about like the bridge to traditional finance. You highlighted early on the call that the AMM concept is expanding into traditional stock markets and Forex, and traditional markets are heavily regulated to protect the retail users. So do you think this algorithm or algorithms like Clever are the missing compliance piece, essentially acting as an automated regulatory safeguard that institutions need before they can fully adopt decentralized infrastructure?
Yeah, exactly. I think you frame it the best. So basically, this is the beauty of smart contracts. So you can say that if you build a good, and I'm saying smart contract, but you think about it as a protocol design. When you think about good protocol design with good incentive structures and rules, if it's good enough, in a sense, it's already a regulation tool. So the way that you can think about it, if you build AMM in a way that it says is only immune against sandwich attacks, so you don't need the regulation for front running because it's already have built-in front running kind of protection. But I think what's happened, and you see it also with regulation environments, is that always you have a arm race that bad users come with new ways to manipulate the system. So in regulation framework, you always come with new regulation to deal with the new manipulation ways that you can trick the government. And in DeFi, it's you need to upgrade the smart contract and come with new versions because you say, okay, the problem with our first version is that you can do sandwich attacks. So if we added slippage protection, now you can't do sandwich attack. And if we add Clever, you now can. But probably after having Clever, someone will come out and say, okay, there is a way to manipulate Clever. So it's the same game, but in a different way. And you described it perfectly. I think mechanism design will replace regulation. Yeah.
Okay, awesome. So next question. You mentioned that deploying Clever on Uniswap v4, hooks or Prof, or other specialized chain. But for developers that are building today, where do you think is the most realistic place to actually enforce this? Like, is it the app layer or the consensus layer, or is it like something else?
Yeah, so it's a good point. I think it's very complex. So in a sense, if you think about optimal, I'm pretty much sure that for any application there is a different optimal ordering rule. But the question is if it's something that we can realistically achieve. So if realistically we can have a blockchain that going to organize liquidity AMMs transaction in one way, liquidation position in another way, and so on. So maybe it's the optimal. But if it's very costly and complex to achieve it, maybe there is a simpler rule that on average doing the best for all the apps or whatever. So I think like I want developers to think about this in a broader way and say, okay, it's realistic to implement those, it's not, if we do domain specific or not, and always think about the trade-offs, or not be stuck that one solution is for sure the best. I think always there is a trade-off. So you need to think about these trade-offs, but I'm sure we can improve what we have currently, that's for sure.
Awesome. My next question is on the concept of gas fee versus splitting. So you mentioned before, like when you split the same thing to too many, like there was a trade-off between splitting too much to the gas fees. So how does this gas overhead impact the strategy, like in comparison in layer ones versus layer twos at the moment? And with the changes in Ethereum, I think it's even more interesting.
Yeah, good question. So I think in general, like mathematically, you can calculate this. So basically the trade-off should be like this, is anytime that you want to split your transaction, you say, okay, if I split it to two, what will be the price improvement? And then I can calculate, okay, I can improving my price can give me in general a benefit of $20. Gas cost of having another transaction will cost me $10 or whatever. So if the conclusion will be that I can do better off, I will split. But as you mentioned, there will be a cutoff that splitting more than that, I will lose money. Now, it's go directly to your second point that it's going to be blockchain specific. So if you have L1 that it's very expensive, so maybe you will split less. And if you have L2 that transaction fees are less than cent or even less or very, very cheap. So it's even better to split because there is no cost. So in our paper, the idea is if there is no really gas fees cost, it's ideal to split as much as you can because there is no cost. So I can send 1 million transaction or one transaction, there is no cost. But in reality, when there is a cost, there is a threshold that you need to stop splitting. Yeah. Which makes sense because then, like there is another problem beside paying gas fees is that splitting a lot of transactions also going to generate a messy blockchain data. So it's not going to be fun to see like in one block there was 1 million transaction from NIR, but it was $1 cent each transaction or whatever. So it's
okay. Less technical question that just thought about now, but like for block builders, is it like much more profitable to kind of run behind the scenes Clever or some other algorithm like that to improve their capital efficiency, and then like they have an incentive to basically not tell you that they reordered it like that, and most users I guess won't even notice. So like how does this affect the incentives around block builders? Yeah.
Yeah, so I think in general, block builders going to have some issues with Clever that it can take some of the MEV profit, and this is one of the problems. However, it can be good if they think about the adoption, because one way that you can think about it is, okay, if there is a Clever, the blockchain will be seen as more reliable, so there are going to be more traffic, so maybe I get less MEV profit, but I get more gas fees profit. So it's a little bit to change the point of view of the block builders, but in a sense now it can take their MEV share. So that's
So for now, like this algorithm is basically is like a bad thing for block builders.
Yeah.
Okay, understand. So my last few questions is more about you. So we would like to get a little bit to know how you started in the ecosystem, or what brought you into Web3. Is it like for the university, or tell us a little bit about your story?
Yeah, so I think like I had a very big luck that my advisor in my PhD, Rod Gerard, one day took me to his office and told me, okay, Nir, there is this liquidity pool, new innovation, go read about it and let's start work on it. And it ended up that it was my PhD paper was about AMM. And I feel like this is the future. It's super interesting and very nice to learn. And I really believe that there is a lot to do in this domain. So it's in the beginning, we can improve it. It's not perfect right now. There is some issues, but it's going to be a very good way to improve the trading environment. And I also want to thank Uniswap Foundation and Labs. They also are very supportive to researchers in this community. So we got a lot of grants and a lot of support for the econ researchers that are doing AMM research, and I think it's really helped us to learn more and improve this.
Awesome. So two last questions. If you have any mistakes that you think other people should avoid, things that you did during your time until you got today, from entering the space until today, you think our community should learn from, or any other tips that you can have?
I think that one issue that we have is that you want to be creative and come with innovations. And one way to be creative and come with innovations is to kind of ignore what you know before, because you need to come with something new. But I think what everyone and many people like always need to remember, that you can do it, but don't always forget like the basics. So I think what you can see, and also it was kind of something that I tried to explain in this lecture, is that even that AMMs are very new and come with a lot of innovations, when people start working with them, no one thought about that it will create the same Flash Boys issues with transaction ordering. So there is a lot of traditional finance stuff that we can learn from, that can help us create a better kind of innovations. And we also need to compare us to those, because this is the way to improve. Yeah. So.
Okay, awesome. So usually we give tips for developers, but this time I would like to ask you if you have any tips for people in the academy, or people just like studying in the university and getting into these subjects. If you have any tips or anything to direct some of our community members in that direction.
So I think it's very important topics, and area of research with a lot of like opportunities. I think if you like it, you can Google search in your university or university nearby who is the researcher that doing stuff that you think is interesting, and don't be shy, email them. Like, I really like that sometimes someone is emailing me and say, hey, I want to work on AMMs, I want to learn about DeFi, and this is the way to explore and educate yourself. Go to webinars like that, conferences, whatever. It's good time to also introduce everyone to Mid-Chain conference that we organize together. With Amit will be this October 26th, right?
Yes.
In Ben-Gurion University. Another good opportunity to someone that is around to come to Ben-Gurion and learn about blockchain and DeFi. And keep working and learning. Yeah.
Awesome. So
Great.
I would like to thank you so much for today, Nir. And thank you for the questions as well. I hope all of you joining us today enjoyed it as well, and you learned something. Nir, thank you again. And some last words for the audience. Just a sec.
Yes, thanks for hosting me and having me, Amit. If anyone has questions, feel free to email me. Yoav, thanks for your questions. And that's it.
Awesome. If someone wants to reach you, what's the best way to reach you, Nir?
Yeah. Google in my Ben-Gurion University email. You will see. I guess it's in the website or something.
Awesome.
Just email
We'll
me.
also add you to our Telegram group later, and if someone wants to tag you there, I think it would be the easiest.
Perfect.
So thank you so much again, Nir.
Thank you.
I'll share the email later in our Telegram group.
Perfect.
But thank
Great.
you so much for joining us today.
Bye.
So, thank you so much for this fascinating talk, Nir. And now I would like to thank all of you for joining us today. If you like this content and you would like to support us, please, I'm inviting you to join us on Telegram and share this with your friends or colleagues who are interested in technical entrepreneurship, in Web3 technologies, and in everything technical in this space. We're here to help you guys with learning from the best, connecting and hiring, and we would love to support and get feedback from you. So just feel free to reach out to us, to any of the managers of the community. We're available also on our website and in our community channels. And if you want to take an active part in the community or speak at one of our next events, please let us know and reach out to us. And for those listening for the first time, so we are the Web3 Devs Underground. We're all about technical content, open source, no shilling, and all done by builders for builders. So everything we do will always be free, reliable, and for the community. We encourage you to follow and subscribe, and to follow on our calendar. There you can see all our next events, and we have great things planned for you in the next few weeks and months. So we would really appreciate your help and support. And that's it. Thank you again for joining us today. I'll put the QR again on the screen so it's easy for you to scan. Just a sec, let me find it. Yes. Awesome. So the next QR code will direct you to our link tree. There you can basically find all the previous events and recordings, and also all our socials. And if you want to reach out to us because you liked what you saw today, so please do. We encourage you to do so, and we would love to keep in touch. And thank you again for joining us, and see you next time.